Welcome to the project demonstration of switched capacitor integrated level step up single phase inverter. So we are using 5 level inverter in this one. 2n+1 means 5 level we are using. So that is capacitor integrated one. So from this and the 5 level signals will be input triggers for this full HVS circuit. So here the process is like we are providing the DC source from this 12 volt 1 amp battery, and that will be boosted with help of this boost converter. And it has a 2 stages. One is the booster converter, this is a full end boost converter, and the next active switched capacitor level we are using here. Right, so boost converter will boost up the input voltage whenever it is not sufficient to inverting purpose. Means though we are providing 12 volt 1 amp constant voltage constant source from this battery circuit, and while we are running the inverting the 5 level, then maybe chance of power fluctuations will be occurred. Power fluctuation nothing but either current or voltage. So in order to stop the voltage fluctuations, we are making use of this boost converter. So the inputs for this boost converter is from this 12 volt battery, and the signals will be getting from our microcontroller from C7 pin. So that will be given to this MOSFET gates to get the sufficient voltage of 12 volts constant, and that is the output from this boost converter, that is to this capacitive bank network with help of this 3 MOSFET circuits. So when we are implementing this in larger scale, these circuits will be multiplied 2n+1 multiplication of 3, 4, 5, 3, 5, 7 like that. As we are using the 5 volt inverter, just one is enough for our project demonstration, and output of this one is making the current constant, and that is input at this HVS circuit. And from here this HVS circuit will convert the 12 volts DC to 12 volts 5 level AC for 1 amp AC signal, and that will be step up with help of this step up transformer. So we are providing 12-0 input to this AC signal, and output is AC voltage of 230 volts. So that is input to our load directly. Though we are using the 12 to 230 volts AC transformer, due to the losses while we are implementing the theoretically circuit to the practical circuit, there will be loss. So that's why we are going to get around of 180 volts to 250 volts around that voltage based on the signals for this MOSFETs and a boost converter. So if you want to get any waveform signals to show in the CRO, just we need to connect the CRO at this bulb output, then we can get the AC waveforms on the CRO directly. So now when we on this, initially this 12 volts DC input parallelly to the boost converter as well as to this PIC microcontroller motherboard, and this consists of 7805 regulator. So this regulator will regulate the 12 volts DC to 5 volts DC, as the operating voltage of our microcontroller is 5 volts. So once it get the 5 volts DC input, it start producing the predefined duty cycles for the both boost and capacitive circuits. So after that it will generate the 50 hertz of clock frequency with 5 levels inverting circuit signals to this H bridge, full H bridge, and from there the 12 volts DC input is converted to the 12 volts AC and step up to the 230 volts and to the load. So here the 12 volt, this battery pack consists of 3 4 volt 1 amp batteries. So in this 4 volt 1 amp batteries are 3 connected in series. So we will get 12 volt 1 amp DC output, and which is rechargeable. In order to recharge the battery, just provide the 230 volts input to this transformer. Transformer will step down the 230 volts AC to 12 volts AC 1 amp output, and we in order to charge a battery we need to provide the constant DC. So that's why we need to convert that AC to pulsating DC first step on this regulated power supply board. So this rectifier will convert the AC to pulsating DC, and to make the pure DC voltage, this capacitor will remove the pulses and provide us a constant DC of 12 volts. So instead of 12 volts, here we are getting around 14.5 volts as we are using the capacitor. After rectification we will get the VRMS value, that is around 14.5, so which is the main charging voltage of our battery. So that is sufficient to charge the battery, and LED indication will show the status of charging. So the battery will get fully charged in a duration of 6 to 8 hours. So till the duration we need to on this charger. So before that, if the battery is getting fully charged, automatically these diodes will block the current flow from the battery to the transformer, as it will become the high potential and the transformer become the low potential. So the diodes will act as a unidirectional current flow. So the extra diode will act as the unidirectional current flow. Right. So let us see demonstration. As we discussed, the operation is like when we on that, initially the light will on and off 2 times. Then after it start producing the signals to this load to convert the AC to step up the 230 volts AC directly, right? So on this motherboard we can see the two major components. One is our reset switch to reset the microcontroller. It won't like erase the program, it just reset the microcontroller. And the next, this one is the crystal oscillator, which will provide us the steel plated one crystal oscillator, which will provide us the 20 megahertz of oscillating frequency to the microcontroller. So the main purpose of this crystal oscillator is, as we have provided the set of instructions to provide the clock signals to these three sections. So these instructions need pulses to execute them, means one pulse per instruction. So we are providing 20 mega pulses per second, means 20 megahertz clock frequency. So controller can execute 20 mega instructions per second directly. So here the ratings are like, this one is a step down transformer, 230 volts to 12 volts 1 amp, and 12 volts 1 amp DC battery, and this one is 12 volts to 230 volts step up 2 amps transformer we are using in our project.